My presentation is on ultrafast method for membrane processing using krypton fluoride excimer laser. Let me first present a synopsis. We developed a novel continuous two-step operation using 248 nanometer wavelength krypton fluoride excimer laser to fabricate polyethylene terephthalate and polyimide support membranes and the final membrane pore filled using hydrogel for responsive behavior. In the first step, membranes with uniform, ordered, and well-defined pores are fabricated using masked laser ablation of membrane carrier films. In the second step, responsive hydrogel is grafted in membrane pores through pulse laser polymerization, or PLP, at different grafting densities induced by a different number of laser pulses. Our results showed that the film thickness has little or no effect on kinetics of PLP for given laser operation parameters when grafting polymerization is performed bottom-up using excimer laser radiation directed from the top of the pores. Our work establishes 248 nanometer krypton fluoride excimer laser as an extremely fast tool for combined laser ablation and polymerization during the same manufacturing process, with the grafting time reduced to a few seconds. The hydrogel network is strongly grafted to the pore walls and remains stable inside them under pressure. The grafting density of the hydrogel in the pores can be tuned by judicious selection of the laser parameters, resulting in room temperature water permeabilities varying by 6 orders of magnitude due to the hydrogel network swelling, deswelling inside the pores. Our results established the novel continuous two-step excimer laser operation as an efficient, fast, and economical method to fabricate responsive membranes. The motivation involves the use of polymeric membrane and membrane technology as a key to solving many day-to-day and high-end global problems. These may involve water purification, batteries, and drug delivery, and our current interest is with drug delivery. For this purpose, we use hydrogels, which have responsive behavior with gating both with respect to temperature and pH values. We use the pH levels corresponding to the variation of pH in the human body, and we use pH between 3 and 7 for that purpose. So we have a fast method for fabricating stimuli responsive membranes, and we are using a krypton fluoride excimer laser to provide well-defined and ordered pores creation in support membranes and grafting of stimuli-responsive transport media in pores. PLP is optimized by control of transport rates through the pores. For this purpose, the fabrication is done in 2 steps, and it's a novel method. So we apply this on either PI or PET films. And in the first step, these support membranes are ablated by using an excimer laser to induce the pores. In the second step, pore grafting of the thermoresponsive or pH-responsive hydrogel is achieved. The use of the krypton laser allows us to tune the parameters, the laser parameters of fluence, number of pulses, and frequency. That gives us pores with macropore morphology. In the second step, by grafting the hydrogel, we convert this to a microporous membrane, and we still have the ability to adjust the number of pulses, frequency for the laser, as well as the solution parameters, which involve monomer, crosslinker, and initiator concentrations to achieve the target solute transport. By doing this, we have shown through water permeation that the permeability could be adjusted over 6 order of magnitude difference. and we were able to obtain thick diffusion where we have the gating action. Current methods for membrane fabrication involve a variety of methods, including electrospinning, track etching, stretching, interfacial polymerization, and phase inversion. Unfortunately, all these methods result in lack of defined geometry, order, and regularity, whereas our method enables us to fabricate ordered, regular, and well-defined pores, which can be filled with stimuli-responsive transport media for controlled transport. And this transport process can be related to existing classical theories, such as the Hagen-Poiseuille equation, which allows us to calculate the flow rate based on the pressure and geometrical and material properties. From that, we can obtain, by using the volumetric flow rate, the permeation coefficient, which then, with the use of a pore density approach, can be normalized with the use of the pore density and pore diameter, and also with the use of the viscosity coefficient for the transport medium, and this is done because it's a function of temperature. Laser lithography is a well-established method which has been used by many companies with the use of masks. And in our case, we are using a metal mesh, to transport a pore geometry down onto a film. And as I mentioned, this allows us to obtain a very well-ordered, well-defined pore path. The laser ablation mechanism itself has been described in the literature extensively. It can involve photochemical ablation, which involves the composition of the polymer structure, subsequent to absorption of the UV photons. So that involves the path 1 shown here, where the molecules and the atoms are transported from the ground state up to an excited state. With the photothermal ablation, we go through a second path here, where internal conversion takes place. In this case, we typically get also a collateral variation of the boundary area, excuse me, and a dark carbonaceous area may develop. The ablation process is described based on Beer's law, where the etch depth per pulse is inversely related to the effective absorption coefficient times the ln of the fluence divided by the ablation threshold. For example, for PET, that is 30 millijoule per square centimeter. We use different film thicknesses, carrier film thicknesses, to see the effect of the film, as well as different mesh geometries, where the pore size varies from 43 to 25 micron to induce different size pores. The schematics of the ablation process is shown in these figures. We have the laser beam coming from the top and going through the mask, which is a metal mesh, and then that geometry is transferred onto the membrane, and we use a vacuum pump to evacuate the ablation products. Since we are doing proof of concept, we don't need a very large area. We just use about 4 millimeter diameter ablation area, which is shown here, and subsequent to the ablation, the film is cleaned by sonication and THF. Pictures are taken of the pore structure using optical microscopy, and then the pore sizes are calculated by using image analysis. Here's another schematic showing the process. Here we see the metal mesh, and this is the film. We have the perforated structure shown here prior and after cleaning. And here's a photo of the same process. The advantages here are that it involves less time it's organic solvent free, which we don't have with the other methods. And we obtain uniform pore size and narrow pore size distribution. So we know that the pore size, the perforation size, is a function of number of pulses. It increases as the number of pulses increase until we reach a plateau which corresponds to the pore size that is being transferred. Typically, the lowest energy for pore depth, pore size, is a linear function, more or less linear function of the thickness of the film. Here, the lowest energy is calculated by fluence times number of pulses times the perforated area. As far as the effect of the mesh opening is concerned, we have shown that larger mesh openings obviously result in larger average pore sizes, cleaner edges with more uniform shape, well-defined pores, and smaller heat-affected area or dark areas. As you can see here, as we increase the mesh size, the heat-affected zone decreases. This is with the PET film, and the same result is also observed with the PI film. So we have already shown the effects of laser parameters on the ablation. And now we would like to look at the parameters both from laser and solution on the grafting. As far as the laser parameters effect on the grafting is concerned, again, we look at the effects of frequency and number of pulses. We know that frequency controls the process time, and the number of pulses will control the exposure time. For the solution parameters, we can change the monomer concentration as well as the cross-linker concentration. Here we see a schematic of the grafting process. It's a bottom-up process. So the grafting solution is below the film, and here's the film, and the light, the laser light comes from the top, and for the pH responsive membranes grafting, we use acrylic acid. And for the cross-linking of the polymer, we use methylene bisacrylamide for the cross-link agent, and the photoinitiator is IrgaCure. For the thermally responsive hydrogel, P-NiPAM, we are using the isopropyl acrylamide, and the curing agent and the photoinitiator are the same as before. With the thermally responsive hydrogel, this material has a lower critical solution temperature, LCST. And for this particular material, it's 32 degrees C. You can see here the behavior. So if you are below the LCST, the material is in a swollen state, so it's expanded. If you are above the LCST, then it shrinks or deswells, and this allows for going from a closed gate to an open gate. And that will occur at the higher temperature. So for the effective laser parameters in the grafting, when we increase the number of pulses, the mechanical strength of the grafted material increases, but also the processing time will increase. As far as the frequency is concerned, as the frequency increases, grafting non-uniformity decreases, mechanical strength increases, processing time decreases, charge density increases. That will be the interaction between the polymer molecules, which will change the response time, their responsiveness, and as a result, the responsiveness will increase. So we can see that we can tune these parameters towards a desired target for gating. As far as laser parameters are concerned for PLP, in this case, the characteristic chain length is given by this equation, which is dependent on the time interval between the successive pulses, T naught, multiplied by the monomer concentration and another constant. So we can see, therefore, that as we increase the number of pulses, the polymerization, degree of polymerization increases, the cross-linking increases, therefore we are having a denser structure inside the pore, which means that the permeability will go down. So if you look at the schematic here, again, that we talked about earlier, we have the grafting solution below the film, and the grafting solution is purged with nitrogen gas to remove oxygen. And the polymerization is quenched with a hydroquinone solution. And the grafted film is immersed in hot water to remove undesired matter. And the water permeation test is done. So you can see here a picture of the grafted material grafted in the pores. So I mentioned the effects of the temperature on the P-NIPAM. You can see that below the LCST, which is 32 degrees for P-NIPAM, the random coil is expanded. And when we go above it, we obtain a spherical globule, which is deswollen. So this is as a result of the H bonding. Below the LCST, dominant H bonding between the P-NIPAM and water molecules results in swelling. And when we go above the LCST, intramolecular H bonding between P-NIPAM chains are more prominent. So obviously, as mentioned, the degree of cross-linking will affect the permeation. Here we see above for the P-NIPAM, above the LCST, we have higher degree of cross-linking, so the permeation will be less. We go below the LCST, that effect will be smaller. So that will depend on the concentration of the cross-linker and the number of pulses. So higher concentration of the cross-linker or higher number of pulses will give us higher polymerization and cross-linking. So this effect can also be tuned, obviously, by manipulating these parameters. For the pH-responsive polyacrylic acid, the triggering mechanism is kind of a reverse of what we see with the thermal response. Here at the lower pH, the permeation is higher, and as we increase the pH, the permeation goes down. This is because the carboxylic groups are protonated at low pH, which leads to intermolecular hydrogen bonding that leads to deswelling. So at pH 3. At higher pH, carboxylic groups dissociate, and this leads to higher charge density in the polymer chain, and that results in swelling and lower permeation. So as far as the effect of laser parameters are concerned, increasing the number of pulses decreases permeability, as we discussed before. Increasing the frequency means compact chain packing inside the pores, and the charge density increases as a result, and responsiveness also increases. Now, the responsiveness, we can judge that by looking at the values, the permeation coefficient values around the gating thresholds. So we can see here that the distance between these two, for example, between the red symbols or the black symbols will change. You can see in this case here at higher frequency, we have higher responsiveness as indicated by the higher distance between those two curves. We also used caffeine molecules to see the diffusion behavior of smaller molecules. In this case, caffeine is 3.8 angstrom diameter. We used the fixed first law of diffusion in terms of concentrations. And the diffusion constant in water for caffeine, we calculated to be 6.11 times 10 to the minus 10 square meter per second using Stokes-Einstein equation. And in this case, for example, if you look at the degree of cross-linking effect, you can see that as we increase the number of pulses, the permeation coefficients will go down as we expected. And also for the responsiveness, we compare the blue and orange colors, and the higher the difference, the higher is the responsiveness. And that's what we see at higher cross-linking cases. For water permeation, we used a permeation cell, a filtration cell as shown here. And the permeated material was weighed in a sensitive balance and was plotted against time. So that then allowed us to calculate the volume flow rate and the permeation constant. For the effect of the porosity, we first realized a couple of issues here. One is the fact that the ablated pores are not perfect cylinders, but they are more like a cone structure. That is because of the reflection and refraction from the pore walls and the amount of time that the light spends at top versus bottom. So the original pore size, let's say, is this value phi. But when we fill the pores with the hydrogel, then the molecules need to go through a tortuous path. So that actually increases the path. So in this case, we need to calculate an equivalent pore size, which experimentally can be measured given the measured volumetric flow rate and other other parameters. From that, from these two values of phi and phi sub g, we can calculate the porosity given by this equation here. So we also realized that the film thickness and the number of pulses also had an effect on the morphology of the grafted material and how it spread at the top of the film in some cases, or protruded out, or more uniform. But in general, porosity versus thickness behavior shifted down towards smaller porosity values at larger numbers of pulses. You can see here the lowest value here. And that's because, again, because the tortuosity increases due to a higher cross-linking and polymerization. So we have this shift of these lines. Now, as far as the effect of film thickness is concerned, we plot the normalized permeation coefficient versus thickness. And in general, the permeability goes down with increasing thickness. And that clearly is seen when we do the normalization that we mentioned earlier. And that's a result that we expect. And the experiments prove that. Now, our basic application is, as I mentioned at the beginning, is towards drug release, and specifically for diabetes, which is a serious health concern. And currently, this is, of course, handled by insulin injection. But we have some issues with sometimes poor patient compliance and control of blood glucose level. So what we have done is, in this case, polyacrylic acid. We immobilize glucose oxidase for pH responsiveness on the polyimide polyacrylic acid membrane. And thus, we obtain this smart gating membranes using this 248 nanometer laser. And the immobilized, this is glucose oxidase, GOD. They show glucose sensitivity and convert the glucose into gluconic acid. And that lowers the pH. So we have a gating activity through that. So therefore, that membrane can be placed over a drug reservoir, and thus the drug can be released through this reservoir or polymer grid in response to changes in glucose levels. So again, glucose oxidase is immobilized, and that creates the gluconic acid, which reduces the pH. So therefore, the permeability will change, as we described before, at different pH levels. So this is, of course, is a self-regulatory method and responds to changes in the glucose levels. So in conclusion, we can say that we developed a simple method to fabricate regular, well-defined and ordered pores. Conditions to obtain wide range of pore sizes in sport membranes were established. We established the versatility of the krypton fluoride excimer laser as a tool for both ablation and grafting. Optimization of pore grafting was achieved for controlled transport rates across the LCST of P-NIPAM and the pH threshold of polyacrylic acid. The method is potentially applicable for fabrication of other stimuli-responsive membranes. For the ablation section, we showed that the excimer laser ablation process is similar for varied thicknesses of PET film. And for the grafting section, we showed that the permeation drops with thickness. The PET film thickness has little or no effect on the pulse laser polymerization mechanism. And under high P, the effect of thickness on temperature response is more prominent. And our experimental results show that by looking into the percentage change on the responsive behavior. For the application for drug release, we showed the immobilization of glucose oxidase could be accomplished on pH-responsive polyimide polyacrylic acid membranes, excuse me, using 248 nanometer krypton fluoride excimer laser for drug delivery. GOD enzyme was immobilized on the membrane using a carbodiimide-based amidation method, and the polyacrylic acid grafted inside the pores shows pH-responsive gating. The immobilized GOD molecules show glucose sensitivity and convert the glucose into gluconic acid, and our experimental results showed that these membranes can detect the amount of glucose and release the corresponding solute amount. So far, we have published 6 different papers on this topic and project. They were published in Journal of Membrane Science, European Polymer Journal, ACS, Applied Material and Interfaces, Polymer, and Biointerface Research in Applied Chemistry. I'd like to acknowledge my co-authors on these, Dr. Ankit Tiwari, who got his PhD on this work, Mr. Lea Wu, who got his master's degree on this work, and Dr. Renuka Patel, who got her PhD on this project. Thank you, and we'll be happy to answer any questions.